Hello, and welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 3, Section 2, Part 2. And Section 3.2 is on heat and thermal energy. So please write this down. Heat is the total energy in a collection of molecules. So all of the energy stored in that sample. And heat is a type of energy, so it is measured in joules, J. And we know joules is the SI unit of energy, and then now we know it's the SI unit for heat. Okay, so we know that heat is not the same thing as temperature. Now we know that. So we know that temperature is the average energy per molecule, whereas heat is the total energy in the molecules. So we measure temperature in degrees Fahrenheit, degrees Celsius, and Kelvin, and we measure heat in joules. So let's look at this. So let's say I have 100 grams of water at 21 degrees Celsius. I'm going to add 33,000 joules, and then I get 100 grams of water at 100 degrees Celsius. You can see the temperature is the same and the heat is the temperature is not the same. You can see that the temperature changes and the heat changes. So this has a higher average kinetic energy of molecules, and it also has a higher total energy in those molecules. So another way we measure heat or energy, not necessarily in science, but more like in food science, is by calories. And 1 calorie is actually like a food calorie is actually a kilocalorie. And if it's a capital C, it's a kilocalorie, and it is equal to 1,000 calories, which are the amount of energy it takes to raise 1 gram of water 1 degree Celsius. So if something is 140 calories, it's actually 140,000 regular calories. So you could heat 140,000 grams of water 1 degree Celsius, or some other variation of that. Another way you can measure heat is in British thermal units, BTUs. And the definition of a BTU is raising 1 pound of water 1 degrees Fahrenheit. So 1 BTU is equal to 1,055 joules of heat. So a BTU is a lot bigger than a joule or a calorie. So something you need to write down, the second law of thermodynamics. The energy, we're looking at energy in the form of heat, spontaneously flows from high temperature to low temperature. So we're going to talk about the system and the surroundings. So this just happens normally if you, where you are at, your body temperature is about 37 degrees Celsius, were to go outside when it was freezing, 0 degrees Celsius, the body heat would naturally go from you to the outside. It's not going to go the other way. So please write that down. The second law of thermodynamics deals with the flow of energy between a system and the surroundings. So the flow of heat is important to almost everything. You, nature, technology like phones and computers. And I would like you to come up with 2 examples where there is a flow of heat energy. And we'll talk about that in class. Okay, let's talk about what a system is. A system is a group of interacting objects and effects that are selected for investigation. Basically, the system is whatever you want it to be. So if I want it to be like a beaker, it's the beaker. If I want it to be a test tube, it's whatever's in the test tube. If I want it to be this whole room, it's this whole room. And then the surroundings is everything in the universe that's not in the system. Okay, there are a couple of different definitions or like categories of systems. One of them is an open system, and that is a system that can exchange energy and matter with the surroundings. So if you have your car doors open, then it can exchange energy and also things, matter. Closed system, a system that can exchange energy but not matter. So no physical things can get out, but energy can leave. So a lot of things are closed systems. Um, like if you have a covered beaker, there isn't any liquid that's going to escape. But if it is boiling, we know that it's hotter than the surroundings, and that heat energy is able to move out into the rest of the lab. So that would be a closed system, which is different than an isolated system, which is neither energy nor matter can be interacted, can flow into the surroundings. So this is like totally insulated, totally walled off from everything else. Okay, I'm going to ask you to make a prediction. Let's say you have 100 grams of water at 10 degrees Celsius and 100 grams of water at 80 degrees Celsius. And then when I mix them, what will happen? So the energy before the mixing is going to have to equal the energy after the mixing. And this is a law of nature. It's actually the first law of thermodynamics. So please write this down. Energy can neither be created nor destroyed. So the energy stored in the cold and plus the energy stored in the hot, when we put them together, is going to equal the energy, that amount of energy. In this big cup is going to have this plus this. Okay, so again, first law of thermodynamics, energy can neither be created nor destroyed. And we're looking at an isolated system. So please write this down. The energy inside of an isolated system is constant. So no energy can get out, no matter can get out. So we know that energy has to stay constant. So please write that down. And then we have a closed or an open system. We know the difference between closed and open is that open matter, physical things can get out, and a closed, physical things can't get out. But in both closed and open, energy can go in and out. So energy can go between the system and the surroundings. So please write this down. In a closed or open system, energy lost by a system must be gained by the surroundings. So you can't ever lose energy. Whatever one thing loses, something else gains. So if the system loses energy, that means the surroundings gained that amount of energy. Okay, looking here in our same example, we had 33,472 joules of energy were in the hot water and 4,184 joules were in the cold water. When we mix them together, we don't lose any of the energy. We get this plus this is 37,656 joules. And then we divide the energy over the mixture. So this is, we're going to learn some of these terms. This is specific heat of water, 4.184 joules per gram degree Celsius. And this is how much the mass is. So when we take these two quantities and we divide it, we get the temperature, which is 45 degrees Celsius. So it's in between the two. So what happens, let you be able to see that. What happens when hot and cold water are not allowed to mix but are allowed to exchange energy? Does one side stay hot and one side stay cold? When does the heat flow stop? So I would like you to make some predictions. And please write this down. Heat flow stops when the system reaches thermal equilibrium. So yeah, so write that down. We'll talk about it. Equilibrium is a dynamic state where whatever is happening on one side going in one direction is balanced by something in the opposite direction. So if 3 people leave the room, that means 3 people have to come into the room for it to be in equilibrium, in balance. So the heat flow stops when the system reaches thermal equilibrium. So you can see we have hot water is going to lose energy when they're right next to each other, and the cold water is going to be gaining energy right until both sides are the same temperature. So I do need you to make this graph. It doesn't have to be quite as specific, but you should have an X and a Y labeled time and temperature, and then a hot water and a cold water coming together. If you notice right at the beginning when there's a big difference, there is a large amount of heat flow. And in the middle or near the end, when there's a small temperature difference, there is not much heat flow. Okay, so something to think about. So if I have 1 gram of water and I put in 4.184 joules, the temperature is going to increase 1 degree Celsius. But if I have 1 gram of gold and I give it the same amount of heat, the temperature increases by 32 degrees. That's a huge change in temperature. Why does water change so slowly and gold change so quickly? The reason is specific heat. So we're going to be writing that definition in a minute. The specific heat of water is 4.184 joules per gram degree Celsius, and the specific heat of gold is a lot less. And so it doesn't take as much heat to raise the temperature when you have a low specific heat, and it takes a lot of heat energy to raise the temperature if you have a higher specific heat. So why would different metals, so we know water and gold have different specific heats, why would different metals have specific heats? A couple of reasons. So looking at silver, its specific heat is 235 joules per gram degree Celsius. Kilogram degree Celsius. And you can look at the last page, we were looking at grams, and that's why in here the numbers are quite a bit bigger because we're looking at kilograms. So whereas aluminum is 900, so aluminum has a much higher specific heat. So if you have heavier atoms, it means in each gram you're going to have fewer atoms per gram. Okay, whereas aluminum is a lighter atom, which means for each gram there's going to be more atoms. And we know that aluminum is a lighter atom because we look at its atomic mass, and it's like roughly 27 grams per mole. And then we look at silver's atomic mass, and it's like 107 grams per mole. So for the same number of molecules, silver is a lot heavier. Each atom is a lot heavier. So if you have heavy atoms, then you're going to have fewer atoms in each gram, and since you have fewer atoms, the energy is spread over fewer of them, which means each atom has more energy, so there's going to be a higher temperature change per amount of energy you put in. And then the opposite would be true for aluminum. You have more atoms, so the energy is more evenly spread out, and there's less energy per atom, so you're going to have a lower temperature gained for each amount of energy you put in. Okay, so please write this down. Specific heat is the quantity of energy it takes per gram of a specific material, and it changes whatever the substance is, to raise the temperature by 1 degree Celsius. So we know that water has a very high specific heat, and it has a very high specific heat because of hydrogen bonding. The answer to a lot of things is hydrogen bonding, and we'll talk more about that later, but briefly, hydrogen bonding is where hydrogens are bonded to oxygens of other water molecules, and because there are so many of those, you have to break all of those before you can raise the temperature, so it takes a lot of energy to raise the temperature. And specific heat is a characteristic property, just like density, boiling point, melting point are characteristic properties of substances. Specific heat is one. And then there is this heat equation. And I would like you to write that down, and we're going to be using that and going through some examples in our next video. All right, thank you.